Hyperbolic functions, section 6.9. Hyperbolic functions include the hyperbolic sine, abbreviated SINH, pronounced sinh, hyperbolic cosine, abbreviated COSH, cosh, etc. They get their name from the identity cosh squared minus sinh squared equals 1, because if x equals cosh t and y equals sinh t, then x and y are points on the right half of the unit hyperbola. X squared minus y squared equals 1, as shown in this here. And that's analogous to the regular trig functions. Cosine and sine are points on the unit circle. X squared plus y squared equals 1. So it's a circle of radius 1. Okay, so hyperbolic functions are useful in modeling some types of decay, velocities of ocean waves and falling objects, shapes of hanging cables, power lines, strands of spider webs, and ideal arches with stable internal forces. Here's definitions in terms of exponential functions. The sinh x is 1/2 e to the x minus e to the minus x, cosh x 1/2 e to the x plus e to the minus x, and the rest of the functions are defined in terms of the sinh and the cosh. So the tanh is sinh over the cosh, coth is cosh over sinh, sech is 1 over cosh, and cosech is 1 over the sinh. So these are very similar to the definitions of the trig functions. And like the trig functions, there are some identities. Sinh of minus x is equal to minus the sinh x, and that's to prove that you just go to the definition. To prove any of these, actually go to the definition. The sinh of minus x just in the formula for the sinh, I left off an h here. The formula for sinh just replace x by minus x. So you have e to the minus x minus e to the minus negative x over 2. Double negative is positive, so this is e to the minus x minus e to the x over 2. And if we factor out a minus 1 from here, we get e to the x minus e to the minus x over 2, and that's just equal to minus the sinh of x. Okay, so that tells us that the sinh is an odd function, just like the sine function is an odd function. And the rest of these proofs are similar. You just plug the expressions into the formulas, into the definitions, so the cosh of minus x is equal to cosh of x. So cosh is an even function. Cosh plus the sinh is equal to e to the x. Cosh minus the sinh is equal to e to the minus x. Also, this is the identity from which they derive their name. Cosh squared minus sinh squared is equal to 1. So I'll go through the proof of that. So the cosh squared minus sinh squared is going to be e to the x plus e to the minus x over 2 quantity squared minus e to the x minus e to the minus x over 2 quantity squared. And we can use the formula for a difference of squares. There's a couple ways of doing this. One way is to actually multiply these out and combine like terms, and a lot of stuff will cancel. But maybe it's a little bit quicker to use the formula for the difference of squares. These are the form a squared minus b squared. A squared minus b squared factors into a plus b times a minus b. So a squared minus b squared is equal to, in factored form, a plus b times a equal to a minus b. So these are the forms something squared minus something else squared. So we can factor this into e to the x plus e to the minus x over 2 plus e to the x minus e to the minus x over 2 times e to the x plus e to the minus x over 2 minus e to the x minus e to the minus x over 2. So this is a form a plus b times the quantity a minus b. So it's a plus b, and this is a minus b. Okay. So so then we can simplify this. These all have the same denominator. We can combine like terms. E to the x and minus e to the x will cancel. So the first factor becomes 2. We have e to the x plus e to the x would be 2e to the x over 2. And the second factor, if we distribute the minus sign, e to the x minus e to the x will cancel. And this will be a double negative. E to the minus x minus a negative e to the minus x. This will be 2 e to the minus x over 2. And then the 2's cancel. 2 divided by 2 is 1, so those will cancel. And that leaves us with e to the x times e to the minus x. And we can add the exponents, use the rules for exponential expressions. So e to the 0, and that's equal to 1. Okay, so so basically all these proofs, you just use the definition in terms of exponential functions to do these proofs. Okay, and okay, so limits are be helpful in graphing if we can determine these limits. A limit is such x goes to 0. So this is a limit. Limit of such x as x goes to infinity. This is limit as x goes to infinity of such x. So this is again plug in the definition in terms of exponential functions. So this is the limit as x goes to infinity, e to the x minus e to the minus x over 2, and that's going to e to the x. It will go to infinity. This is 0 over 2, which is equal to infinity. So there's no asymptote there. Just the limit goes to infinity, though. Limit as x goes to minus infinity. X goes to minus infinity of e to the x minus e to the minus x over 2. If x goes to minus infinity, e to the minus infinity will go to 0, and minus, and then this will be minus the negative infinity, which is e to the infinity, which would be infinity over 2. So this would be negative infinity. Limit of cosh x as x goes to infinity. Limit x goes to infinity of e to the x plus e to the minus x over 2. So this would be infinity plus 0 over 2, which is infinity. Limit as x goes to minus infinity of cosh x. Limit x goes to minus infinity e to the x plus e to the minus x over 2. As x, so the first term now will be e to the minus infinity, which goes to 0. And the second term, e to the minus negative infinity, which goes e to the infinity, which is infinity over 2. So this is equal to infinity. Limit of tangent x. So that's going to be the sinh over the cosh. Sinh x over cosh x. So that's the limit. X goes to infinity. E to the x minus e to the minus x over 2 all over e to the x plus e to the minus x over 2. So the 2's will cancel, and so we'll have the limit x goes to infinity of e to the x minus e to the minus x over e to the x plus e to the minus x. Now this is indeterminate of the form infinity over infinity, but let's multiply top and bottom by e to the x. That'll give us the limit x goes to infinity of, if we distribute the e to x, we'll have e to the 2x minus 1 over e to the 2x plus 1. Actually, no, I want to multiply by e to the minus infinity. So it'll give us 1 minus e to the negative 2x, and 1 plus e to the negative 2x. Okay, so that's better. And then we can take the limit. So the e to the minus infinity will go to 0. So this is going to be 1 minus 0 over 1 plus 0, and that's equal to 1. Limit as s goes to minus infinity of a hyperbolic tangent. So that's again, the hyperbolic tangent is the center of the cosh, and it ends up being e to the x minus e to the minus x over e to the x plus e to the minus x. So this is the limit that x goes to infinity, e to the x minus e to the minus x over e to the x plus e to the minus x. Okay, so let's multiply top and bottom by, it goes to minus infinity here, by e to the x this time. So it's the limit, x goes to infinity, of e to the 2x minus 1 over, this goes to minus infinity, e to the 2x plus 1. Okay, so as x goes to minus infinity, e to the 2x will go to 0. So we have 0 minus 1 over 0 plus 1, and that's equal to negative 1. So the hyperbolic tangent is going to have a horizontal asymptote at 1 as x approaches positive infinity, and it'll have a horizontal asymptote at negative 1 as x approaches negative infinity. Okay, so let's evaluate some values, and this will also be helpful. The limits will be helpful in sketching the graph, and also the being able to plug in values will help in sketching the graph. So if you plug into the definitions, e to of 0, e to the 0 minus e to the minus 0 over 2. So it's 1 minus 1 over 2, which is 0. Cosh of 0, e to the 0 plus e to the minus 0 over 2. 1 plus 1 over 2, which is 2 over 2, which is 1. Tangent, it's e to the 0 minus e to the minus 0 over e to the 0 plus e to the minus 0. So this is going to be 1 minus 1 over 1 plus 1, 0 over 2, which is 0. Hyperbolic cotangent, we just flip the tangent here. We'll have e to the 0 plus e to the minus 0 over e to the 0 minus e to the minus 0. With 1 plus 1 over 1 minus 1, 2 over 0 is undefined. Okay, the such would be 1 over the cosh, so it's going to be 2 over e to the 0 plus e to the minus 0. 2 over 1 plus 1, 2 over 2, 1. Hyperbolic cosecant, we just flip the hyperbolic sign. Be 2 over e to the 0 minus e to the minus 0. 2 over 1 minus 1, 2 over 0, undefined. Okay, we could also evaluate these at 1. So this is going to be center 1, e to the 1 minus e to the minus 1 over 2. And we could maybe get rid of the negative exponent if we multiply top and bottom by e. That'll give us e squared minus 1 over 2e. Cosh 1, e to the 1 plus e to the minus 1 over 2. Again, if we multiply top and bottom by e, we'll get rid of the negative exponent. we have e squared plus 1 over 2e. The hyperbolic tangent is just the sinh divided by the cosh, so it's, and the two e's will cancel. So it's e squared minus 1 over e squared plus 1. Coth, we just flip the tanh. So e squared plus 1 over e squared minus 1. The sech is, you flip the cosh, so 2e over e squared plus 1, and for the cosech, flip the sech. You get 2e over e squared minus 1. Okay, so okay, so let's sketch some graphs of these functions. So you know, it's going to, for purposes of graphing, it's going to be sort of hard to plot at this point here at 1 to the right and up e squared minus 1 over 2e. It's going to be hard to plot that point, but so it's going to be helpful to sort of put these in a calculator and get some numbers that are easier to plot. So e to the minus 2 is approximately negative 3.6. E to the minus 1, I mean sinh of minus 2 rather, is approximately negative 3.6. Sinh of minus 1 approximately negative 1.2, and so forth. So we get a table of values, and then we can plot some points and sketch the graph. Okay, so I made a coordinate system. So the first point, 2 to the left, down 3.6. I should have extended this a little further. It's down negative 3.6, about right here. And then 1 to the left, down 1.2. About right there, and then 0, 0, 1.2, and 3.6 again, and connect the dots. I mentioned before that this is an odd function, and the way there's a couple of ways this shows up in the graph. One is that if you rotate this 180 degrees about the origin, you'll get back the same shape in the same position. And also it shows up on the table of values here. So the sinh of 2 is the well, the sinh of negative 2 is going to be the opposite sign from the sinh of 2, and the sinh of negative 1 the opposite sign from the sinh of positive 1. Anyway, it looks a little like y equal x cubed. Somewhat, I'll say somewhat. It's not exactly the same as, but I'll say somewhat like y equal x cubed, which is also an odd function. And it's good to keep these shapes in mind, especially when we, a little bit later, will be computing inverses, and we have to be concerned about the range and the domain. The range, the range of the inverse is going to be the domain of the original function, and vice versa. Okay, so anyway, let's do the cosh. Again, I have a table of values here, and I can plot the points, and everything is e to the x is positive, e to the minus x is positive, so that, you're not going to get any negative values for the cosh. Everything's going to be positive. Okay, so we have 2 to the left, up 3.8. So that's maybe about right here. 1 to the left, up 1.5. And then 0 left to right, up 1. And plot the rest of the points. Okay, and then connect the dots. And okay, so that's the shape. And I mentioned before that cosh is an even function, and there's a couple ways that shows up. One thing is that cosh of -2 is the same as cosh of 2. Cosh of -1 is the same as cosh of 1. That shows up in the table of values. On the graph, the way it shows up is that the left side of the graph is the mirror image of the right side of the graph. And this looks a little bit like, somewhat like, this is sometimes called the catenary. The shape is catenary. It's somewhat like a parabola. But not quite. So it's subtly different from a parabola. In a later video, we're going to be talking about, when we get into some applications, cables can take the shape of a catenary if there's no weights hanging from it. So here's a catenary. This is and this is the cosh function. It's called a catenary, but it's actually the cosh function. But if you have uniformly distributed weights hanging from the cable, then it's going to be a parabola. So you can see that the shapes are very similar, but they're sort of subtly different, and it's even hard to tell just by looking at it which one is a parabola and which one is a catenary. But they are different equations, but somewhat similar shapes. But anyway, that's we'll get into more about catenaries and cables in a later video. Okay, so the hyperbolic tangent. We said this one had some asymptotes, and so let's. And then we have a table of values here, okay, so I'll draw on the asymptote. We said there's horizontal asymptotes have 1 and -1. If you go out to infinity, you get a horizontal asymptote of 1. Going out to minus infinity, you have a horizontal asymptote at -1, y equal to -1. Okay, so let's then plot the points. 2 to the left, down almost 1, not quite, and then 1 to the left, down about 3/4, 0, 0, 1 to the right, up about 3/4, and 2 to the right, up almost 1, and connect the dots and extend it toward the asymptotes. Okay, so this looks a little bit like a tangent inverse function, but it's not quite the same, but it's somewhat similar. And we said this was an odd function, and you notice that the tangent of -2 is the opposite sign from tangent of 2, tangent of -1, opposite sign from the tangent of 1, and so forth. And the way that shows up in the graph is with the symmetry. If you rotate this 180 degrees about the origin, you get back the same shape in the same position. Domain here is minus infinity to infinity. It's all real numbers. The range is going to be -1 to 1. Okay, and when we work with the inverse function, the tangent inverse, we're going to switch the domain and the range. So the domain would be -1 to 1, and the range would be minus infinity to infinity. Now the coth is the multiplicative inverse, which is different from the function inverse, but it's the multiplicative inverse. So so it's 1 over the tangent, and so it's going to have these same asymptotes, except for the tangent, the graph is going to be a little bit above the asymptote, or on the positive side, or below it on the negative side. And we also have a vertical asymptote when the tangent is 0. As x approaches 0, the tangent approaches 0, but the 1 over the tangent is going to go to infinity or minus infinity. So we'll also have a vertical asymptote there. So let's plot the points here. Okay, so we have these same horizontal asymptotes. We'll draw those in. And we'll plot the points. So it's 2 to the left, down a little bit past 1. And 1 to the left, down about 1 1/3. And you can connect the dots and extend it toward the asymptote. Then we have 1 to the right up, about 1.3, and 1 to the right, 2 to the right up just a little bit past 1, and connect the dots and extend it toward the asymptotes. Okay, so this is the tangent, and yeah, take the note of the domain and range here. The domain would be minus infinity to 0, union 0 to infinity, and the range is minus infinity to minus 1, union 1 to infinity. Okay, and when we switch the when we compute the Coth inverse, the domain and range are going to switch. Such it's 1 over the cosh. Let me plug in my battery here. And again, we can plot, pick some values of x and compute such. Okay, so let's take a look at the cosh. This is 1 over the cosh. So the cosh is always positive. So the such is 1 over the cosh is always going to be positive. So we're looking at the first 2 quadrants here, and 1 over 1 is going to be 1. So they're going to meet at this point here. But as the cosh gets big, 1 over a big number is going to be small. It's going to be close together, so close to 0. So you're going to get something that a horizontal asymptote there for the such. Okay, so let's plot these points. We have 2 to the left, up 0.27. That's up like a quarter or so, and 1 to the left, up 0.65. That's about 2/3, 0, 1, and then it's about 2/3 again, and a quarter. So the graph looks something like this. It looks kind of bell-shaped, somewhat bell-shaped. That's not the usual bell curve of statistics, but it might be one of the unusual bell curves of statistics. I don't know, but it's not it's not the standard normal curve that we usually work with in statistics, but it does look a little bit like a bell. And then the cosec. Let's take a look at it's 1 over the sec. So let's take a look at the sec. as x goes to infinity, this essentially goes to infinity. So 1 over the central is going to go to 0. So you'll have a horizontal asymptote at 0 again. And as x goes to 0, the central goes to 0. So 1 over that is going to go to infinity. So that kind of gives us an idea of what the graph will look like. So let's plot the points and sketch the graph. Okay, so the axes are going to be asymptotes in this for this one. We have 2 to the left, down about a quarter, and 1 to the left, down almost 1, and connect the dots, extend it toward the asymptotes. And then we'll have 1 to the right, up almost 1, 2 to the right, up about a quarter, connect the dots toward the asymptotes. So it looks a little bit like 1 over x, so somewhat like a hyperbola, but the hyperbola. It's not exactly a hyperbola, but it's sort of subtly different, but it looks somewhat hyperbola shaped, somewhat like 1 over x. Okay, so that concludes this presentation.